Okay, welcome to Quantum Curious, and in today's lecture, we are going to consider and discuss two main concepts from quantum information theory, and it is very helpful in quantum cryptography. So, the first concept is the Bloch sphere, and it is a very convenient way to visualize the qubits in spherical coordinates. We could also visualize many kind of operations like Hadamard gate and different of operations and gates on the qubits. And these block sphere helps us in understanding and visualization of the qubits and their different and the actions on the qubits in a very more visual and concrete way. And the second thing we are going to discuss in video is the probability notation and some concepts related to probability theory. So probability theory is very important in quantum mechanics as we know that the measurement outcomes and different phenomena in quantum mechanics are probabilistic. So it is very useful and very helpful to understand some core concepts of the probability theory. So we could write any arbitrary quantum state as in equation 1 with some kind of helpful parameters like gamma, theta, and phi. So you could see that exponential iota gamma is a global phase, and it is usually does not play any kind of meaningful role in different phenomena like measurement of quantum states. So we could successfully ignore it and neglect it in our notation. So in order to prove that it is not that meaningful to write the global phase with any quantum state. So consider we have two quantum states in equation 2 that are psi 1 and psi 2, and we could write psi 1 in terms of psi 2. So it is written in equation 3. So consider we are going to perform a measurement in basis P on these quantum states, and the probability of getting outcome B is given in equation 4. So it is represented as the mod square of the inner product of psi 1 and P, and we could open this mod square and could write in as the conjugate as the multiplication of the conjugate of the inner product and its normal form. So writing psi 1 in terms of psi 2, we could open up this in more detail, and we could see that these exponentials are going to cancel each other. So we get the mod square of the inner product of the psi 2 and psi p. So these probabilities are not that very much different. In fact, they are identical to each other. So we could easily ignore the global phase and could perform measurements on the state given the measurement basis. So the considered states in equation 2 are identical except from the global phase. The global phase does not play any meaningful role for, so we could ignore uh, in upcoming session the global phase in different phenomena like measurements. So we could see that the parameterization that we have used in of the arbitrary quantum state equation form preserves the normalization, and normalization condition is very helpful in checking that whether a given quantum state is a physical or valid quantum state. So we have probability amplitudes. So alpha is equal to cos theta by 2 and beta is equal to iota iota phi and sine theta by 2. And taking their mod square and adding them, we get the answer is equal to 1. So this parameterization that we have used in order to write any arbitrary quantum state, we get the uh, condition of the normalization, and it's fully satisfy the validity and physicality of the given quantum state. So the Bloch sphere is represented as spherical coordinates, and we could see that phi here is the angle that a projection of the quantum state making with the axis x, and the theta angle is the angle that is the quantum state making with the axis z, and we could see that the zero state is along z, and the one state is opposite to it. So consider we have a quantum state with the gamma is equal to 0 and phi is equal to 0. So we have this kind of quantum state in equation 6. So how can we visualize this quantum state in the Bloch sphere? So we could see that phi, if we take phi is equal to 0, so the projection is parallel to the x-axis, and the way we have a freedom to take any value of theta that could goes from 0 to 2 pi. So uh, the quantum state is parallel to the plane xc. So this is how we can easily visualize the quantum state uh, or qubit in Bloch sphere representation. So now consider that how can we visualize the visualize the action on the qubit like Hadamard gate in in Bloch sphere representation. So consider we have a state that is plus state that is the equal superposition of of the state 0 and 1, and we apply Hadamard gate on this it's in the on this single qubit state, and we get a 0 state. So uh, the plus state is along the axis because it is equal superposition of 0 and 1. And when we apply it on and when we apply a Hadamard gate or transformation on this qubit, we transform or rotate it along z-axis, that is the 0 state. So Hadamard transformation corresponds to the rotational transformation in the Bloch sphere. So we could visualize or interpret the quantum transformations as rotational transformation in Bloch sphere. So this is the very helpful way to visualize the qubits and the actions that we could perform on the qubits, like Hadamard gate or any unitary operation in the form of rotational transformation in Bloch sphere representation. So this is the very fruitful way to represent qubits and their actions. So next is the probability notation, and consider we have a variable x that is the discrete variable, and it can take any value small x, consider from a finite set. So the number of values in a finite set of curly x is represented as the mod of the capital X. And the probability of taking any value from this finite set x is represented as the probability distribution function. And we denote it as p of subscript x, and the argument has a small x in it. So the most important thing that any probability distribution should follow is the normalization condition, as we have described earlier, as it plays a crucial role in describing the physicality or validity of the given quantum state. So the sum of the probability of taking value from a set X is should be equal to 1 for to be for the normalization condition to be fulfilled. And if we have a clear concept and from the context of the probability, whether which probability uh, variable or random variable we are taking, and from which set it is taking the value, we can also use the shorthand notation, that is the small p with subscript capital X. So consider we have two random variables. So consider we have two random variables x and y, and they can take value from any finite set x and y respectively. So their joint probability, that is the probability of their interdependence, could be written or denoted as the p subscript xy. And this is not always the case that their joint probability is in a product form. It could be in a product form when the two random variables are independent to each other, and it could not be a product form when they are not independent to each other. So this gives rise to the concept of the conditional probabilities. So conditional probability denoted as in equation 12 as with a special mark, that is the straight line, and it is interpreted as the probability of a random variable x that depends upon the value of the y, and it, it it is related with the joint probability of these two random variables from the base rule that is given in equation 12. So conditional probability concept is very important in describing many phenomena in quantum cryptography. That is, we could say that how much Eve know given the information of Bob, or how much Alice knows given the information of Bob. So these kind of concepts is very could be easily described by the concept of the conditional probabilities. So in today's lecture, we describe the convenient way to represent the qubit, that is the single qubit state or the pure state in Bloch sphere, and the transformation that takes place on the qubit in the form of the rotational transformation in the Bloch sphere. And we reviewed some basic concepts of the probability theory, that like conditional probability and joint probability, that these concepts are very helpful in understanding the security analysis of the quantum cryptographic protocol. So if you like this video, kindly share and subscribe the Quantum Curious channel. Thank you.